we want to ensure that nothing important stays hidden in your data. The retrieval becomes a tool the agent calls in a reason act. It is allowed to requery and reflect until it has enough evidence. So K controls the list length, but not the true relevance coverage. And no single one is best. It all depends on the need you have. Hello, my name is Grzegorz Jurdziński. I'm a senior machine learning engineer here at Deepsys AI, and today I'll talk about recall-first RAG systems and when the standard top K retrieval might not be enough for you. So let's formalize a bit what recall means in this talk. So we'll understand by the system's ability to find every piece of relevant information, and this word relevant will be repeated over and over again today. So we want to ensure that nothing important stays hidden in your data. And this is particularly important in some domains, like, for example, legal, compliance, medical, or due diligence. In these domains, omission is punished more than increased latency and cost. Missing one relevant document can be much worse than reading several extra chunks. That means that when you're building a RAG system, you should first figure out what is your target if you want to focus, if you're in one of these situations when a recall is truly important. So before moving into other details, let's quickly refresh how the standard RAG works. Usually we'll have vector database with pre-computed vectors for documents we'll talk about, and the user comes with a query. This is used to retrieve the relevant chunks from the vector database, and they are scored. So both query is being embedded. We already have embeddings for all the chunks, and we calculate the similarity score. And eventually, in the most standard approach, we take top K, let's say, for example, K equal 3 chunks, and we keep only those 3 most similar chunks to our query, and we pass it to answer generator. All of the other chunks are being discarded. So this creates a hidden dependency. Top K becomes the gatekeeper, and this is where the problem lies. So firstly, top K is practically a raw knob in recall critical domains. So K controls the list length, but not the true relevance coverage. So we decide how many chunks we include in the answer generation, but we don't decide whether we include relevant chunks or not. Also, the similarity, embedding similarity, is pretty good for ranking, so it quite well sorts candidates, but it does not, unfortunately, define a stable pass or fail boundary. And one might think that a simple solution would be raising K, but that yields to a situation when we can flood the generator with irrelevant chunks and distract the context. And a bit more nuanced downside is the chunking loss. For this approach to work well, we need to split the documents into smaller chunks, and in some cases, this can hide related evidence behind weaker local similarity. So let's discuss what alternatives we have, and we'll follow a pretty simple progression. So we already discussed the top K approach. Then we will briefly talk about similarity threshold and cross-encoder reranking. After that, we'll spend a bit more time looking into using LLM as a judge for relevance. And I'll briefly also go over a couple of further ideas. So before digging deeper into LLM judging, let's first talk about thresholding. So this is probably the first and most obvious and simple, of course, fix to our issue. So previously in this step, we took only top K chunks, but since we get the actual embedding similarity score, why not set a threshold? Say, for example, threshold being 0.7, and we take all the chunks that pass this threshold, we discard all the others. So this solves the issue with fixed K. Well, obviously, we have a variable result count. It's very cheap to add. Basically, on retrieval level, we don't need to add anything. The only cost increase is that we might end up passing a bit more chunks to the answer generator. The downside is that the global cutoff stays brittle, as I mentioned earlier already. the embedding similarity score, unfortunately, rarely gives you a good global cutoff. So this approach might be good for modest recall gaps. So when you're in a situation for some reason where piece of context is either relevant or not, and there is no gray zone, there is nothing somewhat relevant. A bit more sophisticated approach is called reranking. So in this solution, we start with a pretty broad retrieval. So in this step, we would choose not the chunks to be included in answer generation, but the candidates. And then we use a model called cross-encoder to recalculate the actual scores. And cross-encoder usually scores jointly query and the chunk. And after that, well, here in my example, we use threshold, we might use top K or whatever. But basically after the re-ranking, so the improved relevance calculation, let's call it, we again somehow decide whether to keep or not the chunk. So this yields, of course, better ordering quality. That's what the whole re-ranking step is for. And the moderate latency cost is and the latency cost is pretty moderate. So of course we need to do this extra step, but usually it's not very pricey. The downside is that it often requires fine-tuning of the cross-encoder, and then more often will frequently need the data, or at least a careful fine-tuning of the option we choose. And it still might miss many nuances. So the approach I recently had an opportunity to work on moves from using a dedicated cross-encoder to using actually LLM as an explicit judge whether a chunk is relevant. So similar like previously, we start by a pretty broad retrieval of candidates. And then we ask preferably a lightweight LLM just to tell us, is each chunk, or is this particular chunk relevant? We make this decision separately for each chunk, and we keep the ones that got answered that, yes, it was relevant, or we discard those which were decided not to be relevant. And the obvious question you might ask is how to keep this affordable. Of course, using LLM over possibly many chunks can be pricey, both in sense of cost and latency. So firstly, we can parallelize this. So we can evaluate each chunk concurrently. So in this diagram, we see this gray box, and we can basically do this all at once. Of course, this trades latency for throughput. But usually, especially if we use LLM provider with batch endpoint, this is very useful here. This is not an issue. Second tweak you can do is batching, but in a different sense. So we can group several chunks in one prompt. This way, we amortize the prompt overhead. So in each prompt, in each query to the LLM, we need to provide the system prompt, we need to provide the user question, we need to explain the instructions. So we save on that in this way. But of course, we need to be careful with this batching, because if we put too many chunks into one batch, we risk lower quality answers. And finally, probably the most important part is shrinking the judge. So I already mentioned that we preferably want a lightweight LLM. So we prefer small models, and we use larger for final answer generation only. So of course, we need to do a fairly simple binary decision. We don't generate any sophisticated text, so we can leave large models for generation. So, well, basically, we optimize for binary decisions. I previously mentioned re-ranking and using cross-encoder. We can use similar approaches, or we can use models for this approach as well. But the upside of using LLM here is the simplicity of this approach from the development point of view. The LLM works basically out of the box. We just need a little bit of prompt engineering, so it's very good for POCs, for example. But it also has some other upsides. Of course, the LLM can get the more nuanced differences. And after that, I wanted to discuss a couple of further directions. Of course, this is not limited to these ideas I will show here, but these are a couple I did consider implementing in my solution. So the first is long RAG. So it groups related documents into larger retrieval units. So there is some trade being done. We trade a heavy retriever, and instead we need a long context reader. The upside is that we, in the solution, have fewer units to search, so the risk of missing relevant pieces is smaller. Then there is a more modern approach, the Agentic search. So in this approach, we let the model try the retrieval. So the retrieval becomes a tool the agent calls in a reason act loop. It is allowed to requery and reflect until it has enough evidence. Although I would like to emphasize here that sometimes establishing whether agent has enough evidence is not easy without a good retrieval. So it doesn't fully solve the problem of retrieving documents. Sometimes we don't know if these are all the documents we need. We can sometimes just establish whether the documents we already have are actually relevant or not, but maybe in some way the database there are more. And of course, it breaks from the fixed top K. It has adaptive depth search and can stop when it thinks the evidence is sufficient. And finally, probably the most straightforward extension on the LLM as relevance judge solution. So we can use the map reduce approach. So in the map step, the judge doesn't only decide whether a chunk is relevant, but it also extracts relevant facts from each chunk. And then in the reduce step, the generator gets all these extracted facts, and it works on a smaller context. It doesn't work on full chunks, but rather just the extracts. So it can produce much better answers without being distracted by all the irrelevant stuff that just happens to be in the chunk. And this actually allows us to fully use the power, let's call it, of the LLM instead, for example, cross-encoder. And as promised, finally, I wanted to leave you with practical decision matrix. So we discussed 4 solutions, and no single one is best. It all depends on the need you have. So top K, of course, is fastest and cheapest, but actually the recall is lowest, or if you choose very high K, technically it's very high, but it's not very precise then. And this solution works well when, in your case, the answer lives in just 1 or 2 passages, and low latency matters a lot. Then a bit more complex solution is thresholding. So it's still pretty fast, pretty cheap. The recall is low, or maybe rather I should say unstable, and works well when relevant chunks count varies by query, but embeddings still separate signal from noise reasonably well. Then even more sophisticated solution is reranking. The latency is increased moderately, but not terribly. The cost is still affordable. So is the recall. We can use this approach when ranking quality must improve before generation, and some extra latency is acceptable. And finally, using LLM as a relevance judge is unfortunately the slowest option, the most expensive, but the recall is also the highest without losing too much on precision. So this is a very good solution when omission risk is critical and you need explicit relevance decisions instead of tuned cutoffs. Okay, that's all for today. If you found this useful, feel free to like the video and subscribe for more. And if you have questions or thoughts, leave a comment below. Thank you very much for watching, and I hope you have a great day.